Yeah, I guess no one's coming anymore, right? So stream of people has almost ended. So I think we just begin, right? We don't have that much time, and we are running a bit behind schedule anyway already. Yeah, welcome to the first talk. I'm very honored to be chosen to give the first talk here. I apologize to my colleagues that this will not be a research talk. This is a talk for you, right? And I encourage you to ask questions during the talk. And I hope that the level is exactly the appropriate level. It's always really difficult because I don't know exactly your background. And your background is probably also very diverse, right? So you have all kinds of different backgrounds. So I want to talk, so therefore it's perfectly fine if you just want to ask questions. I think that has enough time, the talk has enough time in its slot that you can ask questions. So we want to talk, it's not important that we go through all of these things here. These are the things that I prepared. So I want to talk about hazards in circuits. And I first, so you might not have been working with circuits, and that's fine. So I'd want to, but you're certainly aware of Turing machines. So I want to talk about this connection for a short amount of time, then tell you what hazards are in circuits, and yeah, then show you some constructions, some proofs, some ways of thinking and studying circuits. So how are circuits studied and how are hazards in circuits studied? How do these kind of things of arguments work? Okay. So what's a circuit? So a circuit is just something like this. So there's some inputs here. There's a graph. It's a directed graph. There's no cycle in this graph. So it's acyclic. There's some inputs, x1, x2, x3 here. And there's some computation gates. So you think of Boolean values, like true, false, coming into the circuit here at these inputs. And they go into these computation gates. And then the output is computed and forwarded here to the next gates. Here, look at this. I messed it up because this should have an input arity of 2. Right? So think of this as a negation instead. I just drew the wrong symbol here. So here's an AND, for example, takes the x1 and x2, computes the AND, propagates the AND here. This is the negation of x1, and then the OR is computed and forwarded here, and then it has a single output. Yeah, directed acyclic, inner vertices are called gates. They are labeled. That's the degree, and has exactly one output gate. Is that all right? That's a circuit. There's all kinds of different notational ways of writing a circuit, and the electrical engineerings, they have their own notation, and actually different countries have their own notation for their electrical engineers to draw circuits, and it all gets very confusing. So this is why I just chose to put the logical symbols just into these gates. Okay. Now, a circuit computes a Boolean function, right? You just have some input coming from the just a bit string. Output is just a bit. You can think of circuits that have more outputs. We will not think of those in this talk. Yeah, it's just a single output. Yeah, so it has a size, in fact. So now this becomes now very much track A because we are studying some complexity parameter here, right? So it has a size, which is the number of gates that are present in this circuit. Here, size is 6. It doesn't matter if you just count the inputs or don't count the inputs, doesn't really matter. Here, maybe just count the computation gates. So the size of this circuit is 6, okay? Now it becomes even more track A. So there's a circuit complexity now of a Boolean function. So somebody gives you a Boolean function, and what you want to know is what is the size of the smallest circuit that computes this Boolean function, right? So you attach now a natural number, that is the complexity, to each Boolean function that you have on any number of inputs. All right? It's fine? Yeah, see, people nodding is good. So we will study this. This notion here, C of F, is like the fundamental notion that we will study in this talk. The connection to Turing machines, because you know Turing machines, yeah? So, okay, this is just the circuit complexity, but the circuit it has just a fixed number of inputs. Like every circuit has a fixed number of inputs. So how can you set up a connection to actual Turing machines and languages, and that is the following is the connection. So this is just the only slide I'm doing this. So if this is a bit fast, don't worry. We can just go back to circuits in a minute. So you take a language, yeah, and so the language always has a sequence of indicator functions here. So the language is basically a function from 0, 1 star to 0, 1. Yeah, so it's indicator function. And you can just look at the indicator functions, but you take only exactly n many inputs. Yeah, and how do you do this? Like a word is in the language has a length at exactly n, if and only if the indicator function is 1. But now this gives you indicator functions, and each of these indicator functions has, so the nth indicator function has exactly n inputs. Yeah, so what you can do now, you can look at the circuit complexities of these indicator functions, yeah, each of their own, and that gives you now for each indicator function, so given a language, yeah, you get all these indicator functions for that language, and for each one you get a natural number that is its circuit complexity, and that gives you for a language. This is how you go from a language to a sequence of complexities, so sequence of natural numbers that describe the circuit complexity of that language. Yeah, so this is how you can do it. And so there's now a definition of exactly those languages where this circuit complexity grows in a polynomially bounded way. All right, so this is just a fancy notation for polynomial in n. Yeah, this is just a cubic or quadratic or something like that, like any of these. And that is the class P/poly. And yeah, so it's related to the class P. It's not exactly the class P. It's slightly different, but P sits inside of P/poly by saying that if somebody gives you a polytime Turing machine, then you can find this sequence of small circuits that decide the indicator functions. Yeah, maybe. Oh, step. This is a step is with an E. It's not with an A. This is a very Texas way of pronouncing it. Okay. So why is that? So what you can do? So circuits are circuits. As I said, they only have every circuit has a constant number of inputs. But if you have a polytime Turing machine, then the Turing machine comes with that time bound, right? So you know, for example, 5 times n cubed many steps at most on n inputs, right? So this means that you know a priori, before you even run it, you know exactly how many steps the Turing machine can do at most, so that you know that the Turing machine and all its configurations, you have an upper bound on the number, on how long the configurations are. So what you can now do is you can build a circuit that has the configuration on the edges. So I have actually like a 2-line thing. So you have a wire. This is in the circuit, and you have one wire for each pair, position and time, on the Turing machine tape. Right? So you take a configuration at a time step, and it's simulated in that circuit. And the only thing that you need to do is now you take all these different time steps, you put them underneath each other, and have the corresponding little circuits here that simulate how it goes through the Turing machine. So this is if you see this for the first time, it's a bit confusing because I mean you of course want to say a bit more, and I mean I could explain this if I had a bit more time, right? But it's extremely natural to do this. Just having the configuration for one step, for one configuration of the Turing machine to the next, you can implement that in a circuit. You don't have to do a Turing machine for that. And so the whole circuit in the end is also just polynomially large, because each configuration was just polynomially bounded large, and then the time it takes is also polynomially bounded. Right? So the whole thing is still polynomially bounded, just a square of it. Yeah, and it looks a bit unwieldy, that circuit, but that's how you do it. Yeah, in particular, so this shows that P sits in P/poly. And but unfortunately, maybe yeah. So this really says that this is something very, very much track A. This contains undecidable languages. And why is that? Because it's a subtlety of P/poly. where something is in P/poly, like a language is in P/poly. If for every n you find this kind of circuit, but it's not necessary that there's any relation between the different types of circuits that you have for the different n. Right? If you're starting out with an undecidable language, then what you can do is you can build a different undecidable language out of it. Like for every word, say somebody gives you a, so you're starting out with a language, L. So if L is undecidable, say, and then you can blow it up. So you make a different language out of it. So you say it contains all these 1 to the m, such that the word that is so you want m to be in L, right? So you interpret m. Okay, this is now a bit gets really dicey here. M is a number, but also I mean I can just say m in L. So when you interpret this as a binary, as a binary string here, as a bit string. Okay, if you interpret this as a bit string, then it's also undecidable. Because if you can decide that, then you can really readily decide also that. But this one here has a circuit. Whenever you have a language like that, it's always going to have some circuit sequence, and it's basically trivial circuits, because you're just checking if m is actually in L, then your circuit is just automatically says true. If m is not in L, your circuit automatically says false, and it decides it. Yeah, and if your input is not all ones, it also says false. And so the really trivial circuits. So these subtleties tell you that this is not a model to study decidability, yes? Yes, I do, and I think I said that.
Yeah, I came late.
I'm very sorry. Yes.
So, can I ask you a question?
Yeah, absolutely.
But I got affected by your XPC.
Yes.
And then say the XPC and or yes, it's
so you can say so sometimes people also write equals NO of 1 also sometimes. That's a short notation. This is a set of growth functions. It's a set of functions that grow in a polynomially bounded manner. So it's all functions from n to n for which there exists a univariate polynomial that bounds that function from above. And that is this is a set of polynomially bounded functions. And now this is this is now a sequence. You interpret the sequence as a function from n to n, and you say it's polynomially, it's in that set. Yeah. There's numerous implicit type conversions happening here all the time. This is For example, for example, a 1-by-1 matrix and a scalar, for example, I would not convert. Yeah, and these kind of things. This is all implicit type conversions. Yes. Yeah. Yeah. No, you don't have to be confused because the language and the indicator function I treat as the same thing. Yeah, there's no confusion. It's all fine. There's a language and an indicator function. There's absolutely 0 point of making a distinction because there's no interesting thing that distinguishes these two things. Besides the type, I understand that there's an issue here. But there's no other interesting thing that distinguishes these two objects. So it's a language and its indicator function. That's also the same thing. Yeah. Yeah, the undecidability aspect. Oh, that's just okay. We can do this offline. It just says want to make a point that you cannot really use that for making decidability undecidability treatment. This is not very well adjusted to these kind of questions. It is really a complexity type of thing here because the blow up here that you get is an exponential blow up, and but for decidability, that does not matter. But for all complexity questions, this matters a lot. Yeah, so you can Yeah, so it's really made to study complexity. It's not so much made for studying decidability. You can put this back into decidability questions. What you need to do here is you need your circuits here, these kind of circuits here that you get implicitly that are creating these complexity functions here. You need a single Turing machine that on input 1 to the m outputs the mth circuit. If you do that, then have a connection between all these different circuits, and that gives you the class P back exactly. So you can connect it, but the connection always usually goes via, you have to introduce back some model of computability, some Turing machines. Yeah, you have to do that, otherwise you're in circuit in the circuit world, and there a priori you don't study decidability. The interesting thing is that you can still study complexity without having to deal with any Turing machine. Yeah, so the Turing machines are completely out of the picture. You don't have to deal with them. They're gone, and you can still study complexity. So P/poly, of course, could be much larger than P, but it's not. So this is the Cobb-Lipton theorem. If NP has small circuits, then the polynomial hierarchy collapses to the second level. I will not explain that, but what that means. But it is a common conjecture in complexity theory that it doesn't. So we assume that NP does not have small circuits. Yeah. So if you want to say decide if a 3-set formula is decidable, yeah, then there will be no small circuit doing that. Yeah, unless the polynomial hierarchy collapses to the second level. So that's the slide on connecting the P to the circuits. Yeah, and yeah, I thought it would be good to include that. I still do think that it's good to include that. All right, so I want to talk about hazards now, because now since we left the Turing machines behind and we are now focusing on circuits, we can introduce hazards. Okay, so hazards are, this works as follows. You introduce a third value now. Instead of 0 and 1, you also have a u. So u is going to be undefined or unstable transitioning or not yet available, and all these have different meaning. But it doesn't matter. It's just how you think of the value u. The value u is then formally handled in the gates in this fashion. Yeah, if you get u, and you're supposed to take a not of u, it's going to give you u. If you take an and of a u and a false, then yeah, so false is going to be 0 in my talk, and 1 is going to be true, and I will not make it explicit type conversion between the two. It's always going to be implicit. And so here is going to be, yeah, if you get a u, then, sorry, if you get a u and a 0, so if this is, say, a not yet available or whatever undefined value, so say it's not yet available, then you know, though, since one of your inputs is already false, this must output false, independent of what the other input is. Right? So you can output false right away. And these computation gates are implemented in the best way possible that you could actually do it. I mean, you couldn't do it. There are implementations that are worse, where you put also use here and here, but we don't want that. We want the best version possible. Okay, this is the best version. How the gates operate on these inputs. Any question about how the gates operate? You just have a third value now. Okay, and we lose completely the connection to the languages at this point. Yeah, it's just circuits getting different inputs now. And say, for example, the circuit here, and here's the 3 inputs. We call them x1, s, and x0. This is the multiplexer circuit. So the multiplexer circuit, how does it behave? It's this is a selector bit, and the selector bit is either 0 or 1. And the nice thing is that the depending on the selector bit, if the selector bit is 0, it outputs x0. Selector bit is 1, it outputs x1. So it's good to actually take some time to go through that circuit and see that this is indeed what is happening here. Okay, so let's do this. S going to be 0. This means 0 is going to be propagated here. But this means definitely 0 is going to be propagated here as well. Right? F is going to be 0, so this is going to be converted to a 1. So here we get a 1 from one side. X0 is going to be propagated. Yeah. So you get a 0 and an x0. So the output is going to be x0 here. So you can draw a little arrow or not, just doesn't really matter. This is the output gate. Yeah. So if S is 0, then the x0 is the output. And if S is 1, then it's the other way around. Yeah, if S is 1, then you get the 0 here, and then you get the 1 here. So it behaves exactly in the opposite way, and X1 is outputted. That's the multiplexer circuit. And the multiplexer circuit, if you now have both of these being 0, yeah, say both inputs are 0, and your selector bit is now undefined. Yeah, and a desirable behavior would be, well, I mean, it doesn't really matter what which one I look at, is both is 0. A selector bit is undefined, so output should be 0. And in fact, it is. Look at this. If the selector bit is undefined, and say X1 is 0, then here at this end, this will be a 0. Yeah, because we already know it's 0. Right? The undefined value does not matter. So a 0 is propagated to this OR. And here you get a 0, and the S is undefined. So here you get a 0 and an undefined, and the 0 is propagated. So 0 is propagated here from both sides, so the OR is 0 as well. Yeah, exactly how it should be. This is how the circuit works. Behaves exactly how it should. But now, if you get two 1s and the selector bit is undefined, you will not get a 1. That is the crucial thing that we want to study. That is a hazard in this circuit. So look at this. If this is a 1 and the selector bit is undefined, what you get here is a 1 and the U. But if you get a 1 and the U, what do I have to propagate? You cannot, I mean, it's an AND, you get a true and an undefined value, so you have to propagate an undefined value. This is the only choice you have, right? So you propagate undefined value. And the same here, yeah? So U stays a U under the negation. You get a 1 and a U, so you propagate here and also here an undefined value. So at this OR gate, there are two undefined values, and this is an undefined value. Yeah, so this is the U. This is, but it should be what you want is, of course, you want this to be a 1. It's not, right? It's a U. So this is called a hazard. That is called a hazard. Yeah, let me maybe be more precise what a hazard is. So again, so it outputs U. At 1, 1 U, it outputs U. But the Boolean values here, if you replace the U by 0 or 1, you get 1 both times. Yeah, so the desired value here would be a 1 as well. And the definition is exactly that. So you take X being a ternary input, and then a resolution is any way of replacing the U's in the ternary input by 0s or 1s. Yeah, and then yeah, so for example here 0U, 1U, those are the 4 resolutions of that ternary string, and you decide you say when a circuit has a hazard. So a circuit has a hazard if it outputs a U, but it shouldn't. And what I mean by that is there is a bit that it should output. So for all resolutions Y of X, the output is exactly B. So that's the desired output that you want to have at that circuit, but you don't have it because it outputs U for some reason. Yeah. And if it doesn't have a hazard, then it's hazard free. That is the, okay. Any question about that? Yeah, let's have a look. Let's have a look if there's a hazard-free circuit for everything. Yeah. Okay. There's connections to recent papers by people that are also here, also speaking at the at this conference. But I'll not go into that. If you read that paper, you see immediately the close connections to this model of computation. Yeah. All right. Here, let's have a look if we can remove hazards. So here's the implementation of the multiplexer. It has a hazard at 1, 1U. Here is a different version of the same circuit, but I added here this AND gate and another OR gate, and then you can check now that this does not have a hazard anymore anywhere. One can now like go case by case distinction, see that that specific circuit, in fact, is the multiplexer, but without any hazard. And the observation is that this costs you additional gates. Yeah, you need more gates because you have a stronger requirement now on your circuit. Obviously, it's more expensive. Yeah. So this is okay. This is just a remark. So it's a very old paper we found where this has first been done for exactly the multiplexer. So this is a Japanese paper from 1949 where this is the multiplexer here with a hazard, and here is resolved in a different language. Yeah. So this is different notation, but this has been studied. Very old, because obviously you think, I mean, in electrical engineering you might have this problem, yeah, where you flip a switch, but your light bulb was on and it should stay on. And when you flip the switch, you don't want it to flicker. Yeah, you want it to stay on in a constant way. So that's kind of the types of questions. And of course, well, that's for a light bulb. If you have heavy machinery and other things, I mean, they really don't want this to happen. So, that's been very old. And now Huffman's construction. So I want to answer your question now. So Huffman's construction is this theorem here. So every Boolean function, there's a hazard-free circuit computing that Boolean function. Okay, so I'm not sure how. That's fine. We're good in time. I want to show you how this works. Let's look, and I want to show this at an example. So this is the multiplexer, and what I did here is I drew. This is all the different inputs here. It's the hypercube of inputs, just Boolean inputs, and I marked here these 4 boxes here are these coordinates here where the multiplexer outputs 1, okay? And where it's no box, the multiplexer outputs 0. And the standard implementation looks like this, where you have an S and X1. This is like this box here, and the not X and X0 is that kind of box. And it covers all the ones, so you're fine. Now, this implements the multiplexer function, but here's a hazard, and the hazard is this transition here from the red to the blue box. Yeah, so these 2 hypercubes are connected here. So you can fix it by also cover that sub-hypercube by an explicit box. So I have these 3 clauses now, and now this is hazard-free. And in general, this works. So the construction is literally exactly this construction. So you cover the one set. The one set is where it outputs 1, yeah? You cover it with as many largest hypercubes as possible. Yeah, like here, like 3 of them, not just 2 of them. You take all 3 of them, the largest hypercubes that you can fit into the one set. And now and that's it. And you basically these give you clauses. The clauses are describing precisely these hypercubes, and you just put a big OR over those clauses. And the statement is that is hazard-free. There can be no issue here. And in fact, yeah, so each hypercube is decided by a conjunction of literals here. This is what we have, exactly these kind of little conjunctions here, and you make a circuit, which is just the OR of those clauses. Very straightforward construction. And now obvious that there cannot be a hazard anymore where the Boolean value should be 1, because you literally put all these things in as individual clauses. So there's no chance of getting a hazard where it should be 1, but there's still a chance of getting a hazard where it could be 0. And so these arguments now for the hazard-free circuits, they are a bit tedious. And I show you one now and show you how tedious this is, because you want to now also say there cannot be a hazard where the value should be 0. Yeah. So C has no hazard where the Boolean value should be 0. So what you do, it is a bit tedious. So if for a hypercube we have that it's 0, right? So on the whole hypercube, say for example, you look at the 2 boxes, top box here and the box behind, that are both in the 0 set, not in the 1 set. And look at that hypercube. Yeah, so look at that hypercube, and it's 0, right? Then each of our clauses here, these 3 clauses here, they are 0 on every point in that back hypercube over there, yeah? Because they are 1 exactly on these, on where they are 1, right? So on the yellow, the blue, and the red. So they are 0 on that hypercube in the back. And now, since each clause is hazard-free on its own, because it's just a clause, so one can prove every clause in itself is hazard-free, each clause is 0 when replacing the hypercube coordinate here with a u. That's the definition of hazard-freeness. Now each clause is each clause stays 0 even if you replace that variable by a u, but now you take the OR of that and you're done. Yeah. So hence the OR of the clauses is also 0 when you replace the hypercube coordinates with a u. So those are subtle arguments a bit, yeah, and I'm sorry for that, but I do want to give you like an idea of how those arguments go, and this is how those arguments go. It twists your mind a bit thinking about these things. Anyway, this is how it goes, right? It's not long, but it's a bit complicated, yeah. Yeah, so the hypercube has some coordinates here. So a hypercube has some fixed coordinates and some free coordinates, where then this gives you a hypercube. That's the definition. And you're replacing these free coordinates with a u. That's what I mean. Yeah, the fixed ones are fixed, and the free ones are going to be a u now instead. The other ones are still their coordinates. You're not going to changing those. You're only changing the ones where you get the hypercube. Yes, thank you very much for that comment. Yes, this is exactly what you'll be doing. The other ones are fixed to give you that hypercube. Yes. Sorry? The u is on the what bit? Oh, here in this case, the u is here. We only look at the u being on the s. In general, for a definition of a hazard, the u could be anywhere. So this, yes, here on this slide, we did not make any assumption on the u being only on the s. Yeah, here it's arbitrary. So you can have the u. You can have the u anywhere, right? It does not matter where your u is. Right, the first interesting example is the multiplexer, where the hazard is at 1,1u. So this is why this is going to be the running example, but the u could be anywhere and could give you hazards. Yes, thank you very much. Thank you. All right. Now, yeah. OK. Probably not going to do section 5, but definitely going to do section 4. So because in complexity theory, now we are interested. So Huffman wrote the following thing here, and this cannot be read. But in this example, at least, the elimination of hazards substantially increase in the number of contacts. Yeah. So if Huffman's construction, you can actually show that there are very bad cases where this gives you an exponential blow up in circuit size. Yeah, obviously, it's really like it seems like a very stupid idea to just cover every little hypercube, whatever there is, by some explicit clause, and then do a big OR of those. How can this be a good idea? It's not. Yeah, so it blows up the circuit tremendously, exponential size increase, and this is what Huffman already in 57 noted. Yeah, so he wrote his paper on how to remove the hazards. Now, the main question is now this is a track A question, obviously. Yeah, how many more gates do we need to make a circuit hazard-free? So it's possible, but is it always possible efficiently? Yeah. So what you're aiming for is that somebody gives you some circuit, and there's a fixed polynomial, say maybe n cubed, and you only need like that size cubed many to resolve all hazards. So the circuit that you have is hazard-free for the same function, but hazard-free. Something like this. And now I'd like to, yeah. So for complexity theory people, you would now introduce what you are counting here. So CF, remember, CF is the size of the smallest circuit computing a function f, f being a Boolean function on a fixed number of inputs, and CUF is now the smallest size of a hazard-free circuit, yeah, computing your function f. And CUF obviously cannot be smaller than CF, yeah, because every hazard-free circuit is a circuit. And now what you want here is, so if there's a polynomial p, such that for every Boolean function that CUF is bounded from above by p of c of f, right? So unfortunately, you cannot have that unless there's a collapse here. So because then it would follow that NP has small circuits. Right, so that I want to show you how that goes. It's a really neat little proof. Okay, so what you define is the evaluation function. So evaluation function is somebody gives you two things here, which is a 3-set formula and an assignment of Boolean values to the 3-set formula. So an encoding of the 3-set formula, of course, in bit strings, and another bit string of truth values for the. And now you just want to output the value, right? It's really easy to do that as a 3-set formula after all, and just plug in the values, output if it's true or false. Trivial task, and that's the eval function. is obviously in P. It's also in P/poly. This has a small circuit by the construction I outlined earlier. Yeah, the eval definitely has a small circuit. And now we take for eval, we take a hazard-free circuit now. Okay, C going to be the hazard-free circuit for eval. Now, what happens if I feed into that hazard-free circuit the formula, and the truth assignment should just be use? Feed it into that circuit and see what happens. And since it's hazard-free, this is the behavior. So this is literally the definition of hazard-freeness. It gives you 1 if phi is a tautology. It gives you 0 if phi is unsatisfiable, and gives you 0 LU otherwise. This is literally the definition of hazard-freeness. And so since you have that, you can now see if C is small, then yeah, if C is small, then you can efficiently simulate this evaluation here and answer whether or not phi is satisfiable. So you can think, for example, of a Turing machine answering this. So there's a small circuit. Somebody gives you that circuit. You simulate that Turing machine. But you can also so simulate the circuit via a Turing machine, but you can simulate it also via a circuit. Yeah, so therefore, 3-set will be in P/poly if this happens. Yeah, it looks a bit like 3-set would actually be in P, but the thing is that these circuits see that you get, yeah, there's no connection between the circuits. So this is only giving you P/poly, but that's a technicality. Right? But you see that this is extremely powerful. So C will not be small. Even though the eval has small circuits, C does not. Yeah, and now the whole point of why this, yeah, this is the whole point why this was a tremendously successful paper back in the days, is that the theorem above, in fact, holds unconditionally. So yeah, so you do not have to assume that NP is not in P/poly. In fact, this holds unconditionally. So we know that there is no polynomial with this P with this property. We know, and this is much more complicated, this proof, because it's based on fairly difficult work of Rasborov in the 80s on monotone complexity. So this is like a completely different level of difficulty. Yeah, but then you can prove this unconditionally, that the size blow up in the worst case, it must be super polynomial, and in fact actually even exponential. Yes. Sorry. Well, the unconditional one, I think so. I think so. I think so. Yeah, I think it's. Yeah, you need to have the separation. It's a monotone function where Rasborov. So here, what we prove. So the proof goes as follows: you prove that for monotone functions, the monotone complexity is the same as the CU, and then then there's this work by Rasborov, which was earlier, to do exactly the same question, but finding a monotone function with a small circuit and a large monotone circuit complexity. So there is a small monotone circuit, and the monotone circuits are always hazard-free. Okay, so this is how the proof goes. And yeah, is there one of the organizers telling me when to stop? No. So we go until we are told to stop, yeah, which is perfectly fine, I think. There are some efficient constructions because it's like 10 minutes before the break. Or maybe I just give you like a 1-minute thing of this, and then we go to questions, because otherwise we might be messing up the whole schedule. I don't want to do that. Yeah. So you can actually, there are some algorithmic results, also very track AE. Yeah. So some algorithmic results when you know where the U's are in your hazard, and you don't get your U's everywhere scattered throughout, but you know like these are the possible positions for the U's, then you can actually handle them. So you say you have a set S, and you know that only at S those are the positions where the U's are. So how do you handle that? It's possible to handle that. You construct this as follows. So you replace the inputs by fixed constants. So in this example, S contains only the last coordinate. So there's a circuit C, and you know that the U can happen here. So what you do is you put the 0 here, you put this should be actually This should be xn. I'm sorry for that. So xn is the selector, and you're selecting between these two. And this will be hazard-free. Yeah, the selector is going to be the xn. And you can iterate that by saying like you are nesting these hazard-free muxes inside each other. So here the S2 is going to be the x. I think it's the it's the xn, and the S1 is the xn minus 1. Sorry, that's a typo. So it should not be s. It should be the last axis. So you can nest these hazard-free muxes and simulate at these positions. So it's a little neat construction, and we always remove the hazards when you know exactly where those hazards are, where those U's are. And it's also extremely expensive to do that because the new size is roughly to the number of elements in S times your old circuit size. It gives you quite a big blow up, and you need to know where your circuits are, where your U's are. But if you know where, but if the number is say constant, then this is still polynomial blow up. The interesting thing happens on the next slide, where you don't know where your U's are. What to do if we do not know the position of the U's? And now this is a really nice construction, and that's the last thing I want to do. So you have a circuit and just a number of U's, and that could be anywhere. And you want to remove all the hazards that have at most k many U's, maybe because we don't know where the hazards are, but we have some upper bound on the number of U's. And this is how you can do it. So for each subset S of 2k many positions, you CS should be the circuit from the last slide. So it knows exactly where the U's can be, and it fixes the issues with the U's at those positions. It's expensive. 2 to the 2k many copies of your circuit are required for that. And now you build a big matrix, n choose k by n choose k, and the rows and columns are indexed by subsets of size k. And so here, for example, you have these subsets of size 2 and another subset of size 2. And now these are the evaluations of your circuit. And the circuit can handle the U's exactly at the unions. So yeah. And now if you, the key observation here, if you build that matrix, is that, well, the union, well, say your U's appear, they must appear in some of those sets. Say they appear at position 1 and 4, then there must be in 1, 4 here, there's only ones, and in 1, 4 here, there's only ones as well. Say your output is 1, then that circuit here handles this correctly, the U's. Say your U's appear at 1, 4. Yeah, there must be some of one of these will one of these columns and rows will be only have constant ones or constant zeros. And now what you do with that big matrix of circuits that you constructed, you take a big AND of for each row, you take the AND, and the whole total thing is going to be ORed. So what you get is that you take the AND, there will be this one row of constant values, there will just be a 1. There might be ones or U's, so you take the big OR of that, gives you just a 1 in the end. And it also works for zeros, where the AND and the OR is resolved correctly. Yeah, so size estimators, if you do have k being constant, then this is still polynomially bounded. Yeah, because n choose k is polynomial, 2 to the 2k is polybounded, so everything's polynomially bounded. Okay, maybe just to wrap up, because we want to also have Rahul set up at some point. All right, hazards can always be avoided. Yeah, you can always remove them. It's known since 57 that you can do that. It's very expensive in the worst case. It makes the circuit much larger. Yeah, super polynomially, in fact, we know exponentially larger. And but if the number of unstable inputs is just constant, then this construction that I just gave you, that I was admittedly was a fairly quick run through, but this construction tells you that you can remove those hazards, and for constant number of U's, this just gives you a poly-sized blow up. Yeah, so you can still handle that. Yeah, and yes, thank you very much for your attention, and in fact also for your questions and your interaction. Thank you. So usually there's an organizer now here who would ask if there are further questions. Yes, please. Yes.
Does there exist a hazard-free circuit size at most k same function?
Oh, a hazard-free circuit of size at most k. Oh, that is a. So I think we know very little about. So this is the minimum circuit size, almost like a minimum circuit size type of problem. In the circuit, it has a. Yeah, it has, but you're giving the bound and you're asking if there's a. Yes. Oh, I see. Yes, but still, I mean, in the usual minimum. Yes. So in the usual minimum circuit size problem, you're given the whole truth table. Yeah. Here you're given the bound and unary. Yeah, I'm not sure if if anything is known actually about this. No, here you can just you can give the Boolean truth table, and you're asking for a hazard-free circuit implementation, and you can study the minimum circuit size problem. You can about just hazard-free. Yeah, that's perfectly. I think there's nothing known about that. I think there's. I think this is nothing. There's nothing known about this so far. Rahul is, it's over there, yes. So he just came. I think he just came. That's not a fair question. But I think it's a very good question, and I was working a bit towards that with a few students. It's not. I'm not sure. I'm not sure yet. It's not so clear to me. But it's a very good question. It's a very natural question, in fact. Yes, this is so. Yeah, it's a very natural question. One should know something. Yeah, then I think Rahul, you set up, yeah. Yeah, you can ask a question while Rahul is setting up, sure. So people have people defined the circuit classes. I think it is very natural to define these circuit classes. People have defined the monotone circuit classes. There are analogous monotone circuit classes, and you